Let me introduce myself. I'm Pravin. I'm software tools developer in Valeo, Prague. So today I'll be presenting on online video compression for the ADAS recording system. So if you're not from the vehicle background, you may have some of the terms maybe not familiar to you. But don't worry, I'll be explaining those in further slides. So the agenda is like we could first discuss what is the overview of ADAS and what is the recording system and where is this video is coming from that we want to compress. The major part of the presentation will be importing the VHDL IP to the LabVIEW FPGA. So this will explain us like how to import external VHDL IP to our LabVIEW FPGAs. And then we will discuss more on this particular video compression IP FPGA that we imported to FPGA, and then we did the compression of the video in there. And then we will discuss how do we integrate in our existing code, how to modify existing code using this IP. So let's see the overview here. So first, what is ADAS? Is like Advanced Driver Assistance System. And here I am showing the example of Valeo Drive for You sensors. Here you can see the typical vehicles are nowadays getting equipped with the different kind of sensors like cameras and then Scala radars. And what we are interested in this particular presentation is the 4 sensors that are marked here. Those are the cameras, the front view, the rear view, and these 2 are side views. So these 4 cameras are called as the SVS, the surround view system. And as I shown here, those can be used for the top view generation during parking, or for the blind spot detection or the automated parking. And also that can be used with along with other sensors to improve the advanced driver assistance system. So what we will see in the next slide is an example of the automated parking that is achieved with these 4 sensors. So just to give like example how the ADAS and how these 4 cameras are used in real scenarios. So let's take a look at the quick video here. I don't know if you can hear the sound, but yeah. Okay, so this was like kind of example how these 4 cameras were used for the automated parking. Now to have this kind of system working in vehicles, we are at the back end need to have the like rigorous testing and tuning of the algorithm that ECU is commanding the vehicle for automated parking. So it's very important like we test this very thoroughly or tune the algorithms properly before deploying into vehicle. And that's where the recording system that I mentioned in my title that comes in picture. So the recording system, this is one typical at our Valeo. What we have, this is a test car on the right side, and we put the PXI system, NI FlexRIO there, along with which captures from the vehicle the streams of these 4 cameras. You can see here each FPGA card handles 2 cameras, and then there are other sensors like CAN, LUX, LiDARs. So those are all captured through the PXI, all synchronized, and then the whole data, entire video, and all other sensors, that information is stored on the RAID, and that is further used in our HIL system to tune the ECU algorithms, so that we can test it for like different kind of weather conditions and different kind of road conditions in our laboratory after capturing all this information. So point here is like for the recent project we are about to capture 7 petabytes of data in next 5 years, and that's a huge data which costs like millions. So what we did here, we put the third-party compression IP on this FPGA so that we compress the video streams online before storing to RAID. And this has resulted 40% data size reduction, and that ultimately saved money for us. And also like other advantages, like it reduced the FPGA to host transfer bandwidth, so that also made our code lighter and faster in execution. So so let's see on the next slides how to import any VHDL IP first. So before going for this third-party IPs, how to import, let's see how to import any VHDL IP to LabVIEW. So let's see what are FPGA IPs. So if you look into your FPGA palette, you can see there are different IPs are already there. More than 70 are shipped with the Xilinx FPGA with the LabVIEW installation. There are thousands that are available in the market that are compatible with the Xilinx FPGA that NI uses, and those can be paid or those can be free. So if you look more closer to some of the IPs or most of them, you can see the interface is mentioned there for this particular IP, how to communicate from your LabVIEW FPGA. So you can see there, it's either AXI4 stream or AXI. So what is AXI interface? So AXI is used for data streaming in and out of the FPGA. So whatever the IP that you are going to put there, how do you communicate with that, read and write data to and from it, is through the AXI interface. And there is other interface that is typically used is APB interface, which is used to program the IP registers, that is for the configuring the IP, configuring the settings of the IP. So before we go more into details, we need to understand these AXI and APB interfaces. So I will show you in quick, like what are the AXI interface. So AXI was first adopted, it's like advanced extensible interface adopted by Xilinx for the starting from Spartan 6 and Vertex 6 devices. AXI is a part of the ARM family, and the latest version released in 2010 that includes AXI and AXI4. These are the 3 different types of the AXI4 interface. So AXI4 is for the high performance memory map requirements. AXI4 Lite is only for like low throughput memory map communications, like for example to program or control the registers. And AXI4 Stream is like high speed streaming applications, like in bursts you can send and receive data from the IP. So more details you can actually find on this particular PDF online on the Xilinx website for this particular interface. So it's important like how we implement this particular interface in LabVIEW. So the basics of this AXI IP is like it has 3 inputs, 3 outputs. So it acts like a master, and this is like downstream node is like a slave. So master sends the data along with the data validity command, and then slave informs upward whether he is ready for the ready to accept the data or not. So this is quite similar to the 4-wire communication protocol, if you are aware of that. But the difference is the AXI interface informs about the current cycle readiness of the, so in particular, let's say if you put it in single cycle loop, it informs the current cycle readiness, as against the 4-wire informs the upstream block about the next cycle readiness. So how do we implement is it depends on like your upstream and downstream nodes. So if both are AXI, you could implement with this. So the difference is like you should put like the shift registers in between. So that holds the state in between, so that the whenever downstream node is ready in that particular cycle, it can get the data there. So that's how we could implement this in LabVIEW. Your typical application may look like this, where 4-wire to AXI4. So if this is IP that you are bringing to FPGA, which is AXI4, and this could be your FIFOs that are going to transfer data from some other loop to this particular IP. So this will be like 4-wire, and this is like AXI4, and the way you could transfer is with this same, like in between the shift register, and then it informs the upstream node about the readiness, and then it reads the data from the shift register. Similarly, if you have like IP2 outside to your FIFO, it can be done like this. So that's how we can implement the AXI interface in the LabVIEW FPGA. Then looking at the APB interface, it's advanced peripheral bus, which is low cost, minimal power consumption, and reduced interface complexity. So this is used mostly for the programmable control registers or the peripheral devices. So if you want to, like, this particular IP might have the some settings parameter that you want to configure before deploying that or starting that IP. So the APB interface will program its registers from the host side. Some more details on the APB bus specifications can be found at this link. How do we implement this APB? So this is how we implemented recently the APB in our FPGA. So the specifications tells us the two states, like how to the write transfers and read transfers. So how do we write the data to the control registers of the IP, and how do we read the registers of the IP? So it's a typical state machine. You can see we can implement like this, the following this timing diagrams. So I will not go in more detail, but that's how the implementation will look like. So now going further to how do we import the IP to FPGA. So let's first consider the built-in Xilinx IPs. So those that are available through the palette. So that is like quite simpler. You might have already tried it already. So that's just a drag and drop, and then it will give up the pop-up utility using which we can configure the IP. And internally it takes care of the AXI and APB interfaces. So there is nothing much that is needed. You can transfer the data to that particular IP through the FIFOs and read out through the FIFOs. So that's for the built-in IPs. Now coming to the main, the VHDL IPs. So if you find any VHDL IP open source at the outside, which is free, so you have like VHDL source code there. So the way we can import those in LabVIEW FPGA is using either clip node or integration node. So the clip is like it has two types, like the user-defined clip and the socketed clip. So the socketed clip has the ability to talk to your IOs as well, and then it can communicate to your FPGA VI. As against the user-defined clip, it can only talk to your FPGA VI. So this clip is basically appears in your LabVIEW FPGA project properties. And the integration node, it works in a LabVIEW data flow model. So similar to other VIs or other palette items, you can put them on the your data flow model, and then IP can work there. So what is needed, what are the file types are supported for this are the VHDL. So the IP that you have open source outside, it should be either in VHDL format, or it can be in Verilog format, or it can be in netlist files or the Xilinx IP configuration. and then those can be used with these utilities, either clip or integration, to import them into the LabVIEW FPGA. Now, third-party IPs. So typically what will happen is the IPs that you get outside from the vendors, those will not be open source, that you will not see the VHDL code or Verilog code in there. And those are typically encoded in there by their proprietary algorithm. So there are some extra steps that are needed to import those into the LabVIEW FPGA. And those are converting an IP to netlist format and then creating a black box VHDL wrapper. So after these two steps, and the output produced from these steps can be used in the previous step as a clip or the IP integration, and then that can be imported to LabVIEW FPGA. So we'll see these two steps here. So converting an IP to the netlist format. So if you go to your NI FPGA LabVIEW NI FPGA folder on your C drive, there you can find the under programs, the Vivado. So if you launch that, the Xilinx Vivado tool will launch. So this is actually used by the LabVIEW compilers at the backend already, without we knowing us, but it's there. So we have to do this here. After opening, it asks you for some settings and some configurations. It asks you to select the type of your FPGA, its part number. So more details about your particular device can be found here. And after you put that part number there, you need to run the synthesis, like take those encoded files you received from your vendor, and then we have to run the synthesis and then export the output as a EDF netlist format. So EDF is actually a netlist. So actually your vendor can also directly provide this EDF netlist for you. But if not, if they give you only the VHDL files, you can generate the netlist using this step here. So once the netlist is generated, the next step is to create the black box wrapper. So for this particular step, we need to have some basic VHDL knowledge there. Here, what happens is like this wrapper enables us to expose the ports of the IP. So basically, here, let's say Valeo compression wrapper. This is a like black box VHDL wrapper we are creating, and the compression wrapper SIT user is the third-party IP. So basically, we are importing that as a black box here, and then we are connecting the ports using this port map command here to the to our wrapper. So this is the kind of a typical architecture of any wrapper will look like. And with this, then if you put them into the LabVIEW FPGA, it will know the ports of the actual IP, and then through this wrapper, it can communicate to the encoded IP. Yeah. So now, with this, I will show you how is the video compression FPGA IP that we use look like. So what is the ideal compression and decompression IP? So it should be like a lossless compression for our case. It should not lose any data, or like when we decompress, it should produce the exactly same data that we captured. It needs to have a high compression ratio, because like if we are putting that on our FPGA, and if it doesn't put outcomes like high compression, then it may not give us that benefit. So it needs to have like high compression ratio. Then also it needs to have a low FPGA footprint, because we might have like our other code also that captures the cameras, and then there is other logic. So it ideally needs to have a very low footprint. Then there is a context memory that internally any FPGA IP has. So it needs to have the low memory requirement. Then it needs to have the high compilation frequency. So that it compiles at different cameras, different FPS. Also, like other requirement that we've needed is it needs to have a GPU or CPU model also, so that for our cells we can use the GPU model of this IP, or there is a way we can compress and decompress on our CPUs. So that's the requirement there. And it needs to have a multi-instance or reentrant execution. So, for example, our one FPGA handles 2 cameras. So it needs to be able to, we should be able to put multiple instances on FPGA as well on our CPU to run at a parallel. So that's how we like define the requirements, what we want from the IP. And then we did a thorough search. We verified different IPs, different vendors, and we selected Valet IP here, which seemed to meet most of the requirements here, which had like more than 40% compression ratio. It has a very low footprint. We could actually fit the 4 instances, and it has a compilation more than 150 megahertz. So that we could put like 5 megapixel camera at 30 FPS was possible, like, and we put like 4 instances there. So if you see on the right side here, we can see like this particular IP has a AXI interface for the input and also the AXI interface for the output. And there is an APB interface to program its internal registers. So, and as we already seen previously, like we could implement those interfaces in LabVIEW FPGA to communicate with that particular IP. So we'll not see more details like what is this internals of the encoder, decoder, but the main thing is like the interfaces that I want to show here. And then how we can integrate this particular IP in our existing code. So let's say you have a, and this is your existing code here, for example, and we can send the data over the target scope 54 to this particular IP here. So this IP runs, you can put on the LabVIEW FPGA block diagram and then send through the target scope here, and then it sends the output over the target scope 54 to your host. So it can send the compressed data to your host here. So here the supplier has taken care of everything, the AXI APB interface internally. So we actually didn't have to implement the interfaces that we discuss here. But some other IPs that we tested, we had to implement that particular interfaces outside here so that we can communicate to this IP from our main loop. So it was quite easier here in this case to read and write to the IP here. And this is the compression, and then for the decompression, it was similar. In the reverse logic, we could read from the host the compressed data, and then we can send over the target scope 54 to this decompression block, and then decompression block was sending the decompressed data back to your code or outside world for our testing. So again, the same, the interfaces were taken care internally. We just have to send some settings over the host, from the host or to this particular IP. So yeah, so this is pretty much I have. So I would like to take questions now if there are any. I'll be available in the sessions, in the breakout session, and we can talk. Tom, are you there? Okay, let me see here. Some questions. Would it be possible to share the wrapper VHDL code to the community? Yeah, that's pretty much a standard code, and yes, we can share that. And which file format you use to save the data, TDMS or MF4? Yeah, generally we use that format, but for this project we use the MF4 format actually. Okay, maybe for the more interaction, probably we could meet in the breakout session, and it will be like we can discuss more if there are any questions. Okay, so Ali is asking to transfer all the data from RAID. Do you use some kind of removable storage? Yes. Yeah. So it's like the RAIDs are part of the PXI. So those are like put in the slots, and then we take those slots out, and then we transfer to our clouds. Yeah. So yeah, I'll be there for next 10-15 minutes in the breakout room. If there are any questions, we can join there. So thank you very much, guys. Thank you for joining, and have a good day. Bye-bye.